So hello everyone, my name is Scherrer and I will be presenting our work on incentivizing stable path selection in future internet architectures. This work has been done in collaboration with Markus Legner and Professor Adrian Perrig, who are my colleagues at ETH Zurich, and with Professor Stefan Schmid from the University of Vienna. Let me begin with the central question that our work tries to answer. In recent years, there have been proposals for future internet architectures with end-host path selection. And we call these architectures so-called path-aware networks, or short PAN architectures. And a prominent example of such an architecture is the SIGN architecture. Such PAN architectures allow end hosts to do load adaptive path selection, and the hope is that through this load adaptive path selection, the resulting load distribution on the internet will be more equal, and thus the resource utilization can be increased. However, it is also well known that if load adaptive path selection is based on outdated load information, this load adaptive path selection may lead to oscillation. And such outdated load information is basically present in any real system. In order to see how such oscillation could arise, let's look at the following example. In this example there are two paths, alpha and beta, and this diagram will show the load on both paths over time. In the example, the agents continuously select which path that they want to use, and they prefer the path with the lower load. So if there's initially more load on path alpha, there will be migration of agents from path alpha to path beta, such that the load on path beta increases. At some point, the load on the path would be equalized, but since agents only have outdated load information, it will be only after some time t that the agent perceives that there has been such an intersection point. And by that time, path alpha will already have become the path with the lower load, so the more attractive path. That's why the migration pattern is reversed, and this kind of over adjustment happens over and over again. And this is what is commonly understood as oscillation. So the question that we're asking is, how can stable path selection, that means path selection that does not lead to this kind of oscillation, how can it be guaranteed in future internet architectures with end-host path selection? There has been much traffic engineering research that tries to solve a similar problem, namely the stability problem of load adaptive path selection. However, all these schemes are unsuitable for a path-aware internet, and I will explain why by presenting two classic approaches of traffic engineering. So traffic engineering schemes are traditionally targeted to an intra-domain context, so that there is the assumption that the network is in a domain and the domain is controlled by a network operator. This domain has some ingress routers, it has some egress routers, and it has some intermediate nodes that form a network. In this domain, the routing protocol assigns flows to paths, and whenever there is a strong increase in the volume of one flow, other flows along that path may be heard. For example, here flow F12 grows and flow F11 is heard by this growing. Now, in this scenario, the goal of traffic engineering is to reassign flows or shift flows to other paths where there is lower load. For example, here in this scenario, the adaptive traffic splitting ratio would try to shift flow F11 to an alternative path with lower loads. For example, here this path over N4. And of course, this shifting has to be done in a manner such that it doesn't lead to oscillation. Now the problem with applying this idea to an inter-domain network, so domains where traffic flows over multiple domains with multiple network operators, is that if end hosts can select the paths, flows are actually bound to use certain paths, so they cannot be arbitrarily reassigned to other paths. There is another traffic engineering approach that is more compatible with end-host path selection, and this approach consists of having this flow shifting logic at the sources. So this flow shifting logic comes in the form of path selection strategies, and these path selection strategies, or PSS, are crafted such that no oscillation arises. For example, such a PSS may limit the amount of traffic that is shiftable per unit of time. However, there's also a problem with applying this idea to an inter-domain context. Namely, the idea is that in an interdomain context, the source is not an ingress router that is under control of the network operator, but it may be an actual user that sits in another domain. So in a PAN internet, basically the sources have to be assumed to be uncontrolled and to be self-interested. That also means that basically the path selector does not just adopt any path selection strategy that the network operator wants to adopt. Instead, this path selector or this source has a will of its own, and it will only adopt path selection strategies that are optimal from its individual perspective. So what we're actually trying to solve is a game-theoretic challenge, and this game-theoretic question is whether the path selection strategies that have been designed for stable path selection in an intra-domain context will be adopted by self-interested sources that arise in an inter-domain context. In a more game-theoretic jargon, the question we could pose is, do these stable path selection strategies form a Nash equilibrium? What's important to know about these stable path selection strategies, or these path selection strategies that do not lead to oscillation, is that they're basically all following the same idea. So here, this non-oscillatory PSS proposed by Fischer and Föcking makes the path switching probability linearly dependent on the load difference between paths. So the larger the load difference between an alternative, more attractive path and the path that an end host is currently using, the more likely the end host is to switch to the more attractive alternative path. And the important thing to avoid oscillation is that this coefficient in this linear formulation must not be too high to limit the migration rate or the migration volume per time. And this is basically reflected in all the other schemes that try to avoid oscillation. The key idea is always to reduce the migration rate between the paths such that there is a strong congruence between between the network state as it is perceived by the agents and the network state as it actually is. The other thing that is important to keep in mind, what I've mentioned before, is that self-interested sources will only adopt PSS that are optimal from their individual perspective, or more formally, PSS that are so-called PSS equilibrium strategies. In the paper, we formalize this PSS equilibrium as follows. So a strategy is a PSS equilibrium strategy if under universal adoption, so given that every end host in a network adopts the strategy, there is no other strategy that would allow an individual end host to reduce its cost. So cost here means, for example, the expected latency, the expected throughput, and so on. So if there was such a more attractive alternative strategy, then the agents would start to give up their original strategy in favor of the more attractive alternative strategy, and the original strategy would not be a PSS equilibrium strategy, and it would not be a strategy that can be expected from self-interested sources. So in the game-theoretic sense, the question that we're asking is, are these non-oscillatory PSS equilibrium strategies? And as our incentive analysis in the paper shows, is that they're in fact not. So what this means, that under universal adoption of a non-oscillatory PSS, so a PSS that avoids oscillation, it actually becomes worthwhile to adopt an oscillatory PSS, so a PSS that will provoke oscillation. What we conclude from that is that it's very hard to guarantee stable path selection by purely relying on the decisions taken by end host. Instead, if a network operator wants to avoid oscillation, then it must actively incentivize the end host to adopt a stable path selection strategies with so-called mechanisms. And that's where our concept of incentive-compatible stabilization mechanisms comes into play. The goal of this mechanism is to basically achieve stable path selection even in the face of self-interested path selectors. More precisely, the idea of these mechanisms is to alter the cost of PSS such that a non-oscillatory PSS actually becomes a PSS equilibrium strategy, which it would not be without a mechanism. And this cost alteration by a mechanism can be achieved with monitoring, by imposing punishments or requirements on end hosts, or by offering rewards, etc. In our work, we designed two stabilization mechanisms and formally proved their incentive compatibility. And these mechanisms are the FLOSS mechanism and the cross mechanism, and I will focus on the FLOSS mechanism in the following. So the FLOSS mechanism is based on offering a reward to loyal flows. The FLOSS mechanism proceeds in intervals and is based on registrations. So in order to use a path, an end host must a registration for that path for a given time interval. If an end host uses a path in an interval without having a registrations, its packets would be dropped. The key is that registrations are only selectively granted. So loyal end hosts that have already been using a path may always use it again. So they can always obtain a registration for the next interval too. However, new end hosts or end hosts that have been using an alternative path may not always get a registration for another path. Instead, the volume of registration that is available to this new end host is limited. And this is done to avoid exactly the arbitrary path migration that would lead to oscillation. Another key point is that this volume of available registrations, and thereby also the migration volume per interval, is always determined such that the network iteratively achieves equal load. In order to see how exactly this happens, let's look at the following example. So if there is an oscillatory network, the FLOSS mechanism will announce at time t prime that every end host must register for one path that it can use during this upcoming interval I0, starting at t0. So at time t0, every end host will use the path that it has registered for. And this will already lead to some kind of equalization, but this equalization may not be perfect. During the interval there is no migration because every end host only has a registration for one path. But towards the end of the interval, the agents on path alpha will perceive that path beta has lower load, so they will want to try to migrate to path beta. They will apply for registrations there, but only a subset of these registrations will be granted. So the load gap between these two paths is reduced, but it's not inverted. So there is no over adjustment. And this idea is applied multiple times until the load is equalized to a degree that the agents perceive no load difference anymore between the paths. So that also means that they don't see any benefit anymore in migrating. So at that point, the enforcement of the mechanism can be suspended and the network is on equilibrium on its own. So that's how the FLOSS mechanism incentivizes stable path selection. So to summarize, for the stability of load adaptive path selection, we have seen that there are some schemes that achieve this stability but that are incompatible with end host path selection because they use a hop-by-hop forwarding principle. There are other schemes, these path selection strategies, that achieve this stability and are compatible with end host path selection, but what we show in our paper is that these schemes are not incentive compatible, or they are not rational path selection strategies given self-interested sources. And what we contribute in our work with these two mechanisms is that we have schemes that achieve stability, are compatible with end host path selection, and are actually incentive compatible. So they are guaranteed to work in given self-interested sources. And this game-theoretic perspective that we add in our paper to this classic question is a perspective that is very important to consider in upcoming path-aware internet architectures. So with that, I'm concluding, and I'm looking forward to your questions in the Q&A session.